So welcome everyone. Welcome to Strait Science. Strait Science is an evening science seminar series produced by University of Alaska Fairbanks Northwest Campus and University of Alaska Fairbanks Alaska Sea Grant. You're in the home office, or not the home office, you're in the work office tonight. And both Northwest Campus and Alaska Sea Grant, we are public servants of the Bering Strait region. We serve all peoples of the Bering Strait region, which is the homeland and waters of the Inupiaq, St. Lawrence Island Yupik, and Central Yupik peoples. So tonight, I'm calling from a building that is affected already by permafrost. We're tilting like crazy, and it's gotten a little worse in the last couple of weeks. And tonight's speaker is Guido Grosse. He is head of the Permafrost Research Section at the Alfred Wegener Institute's Helmholtz Center Permafrost Research Station. So if there's anyone qualified to talk about permafrost, it seems like we've got the man to do it. And he is calling tonight from Potsdam, Germany, and I had to look that up where it is. And that is known as, just so you know, Guido, it's the capital of Brandenburg, Germany, and it is the land of palaces, lakes, and gardens. So it sounds lovely and an interesting place to be a permafrost expert. So that takes you out of that, I would think, not out to the world of other things. And he is tonight, at the end of this, show a little love, not now, wait till the end of his talk. But we are 10 hours ahead of you, I think.
10 hours behind, actually.
Yeah, it is currently 4:32 a.m. for Guido, and he is giving us this Strait Science to all of us in the region. So we really, really appreciate your perseverance. With that, Guido's been doing research on the Baldwin and Seward peninsulas on permafrost, and I'm gonna let him. He said he has a slide with a full introduction for himself, so I'm gonna let him speak for himself and let us get underway. But thank you so much, Guido. And I don't think you're probably one of the furthest callers we've had, and one of the furthest presenters we've had, and certainly one of the most time challenged. So thank you so much for being here. Take it away.
Thank you very much, Gay, and thanks for the invitation. It's exciting to present here despite poor timing for me. I really like the region, Western Alaska. I'm very much connected to it for a long time now, and that's why I'm really interested in giving this talk, even it's very early in the morning here. We'll be talking about permafrost thaw and permafrost observations in Western Alaska. And we call our campaigns that we did for the last couple of years now, Perma-X, and Perma-X stands for permafrost exploration, basically. And so there are a number of people involved in these campaigns beside myself. Many of them are from AVI, but there are many collaborators as well. I only name one person here, Caitlin, who was involved last year. She's actually a local from Kotzebue, and she was studying at UAF for a master thesis project. And so she was involved in the campaign last year. What you see on the picture here, the first slide basically is a permafrost lake, and that's a specific lake that thaws into permafrost, and that's one from the Seward Peninsula, actually. And so we are studying landscape changes that are associated with thawing permafrost, and lakes play a big role there, but there are many other processes and features that are important for thawing permafrost. And so I'm going to dive into this a little bit more over the next, sort of an hour. And we use a lot of remote sensing. And so most of my presentation will be about our observations from airborne campaigns, so with an airplane, but also with satellite data. Okay, a little bit more about my background. So why am I connected to Western Alaska, and why am I interested in this region? I'm a geologist by training, actually. So I studied at the Mining Academy in Freiburg in Germany. I did a PhD in geology here in Potsdam in 2005. And then I actually moved to Fairbanks, and I lived in Fairbanks for more than 7 years. I became a postdoc there and a research assistant professor. studying permafrost in Alaska. And so that's when I started working also in Western Alaska, mostly on the Seward Peninsula, being based out of Kotzebue or Nome, and then working in the northern Seward Peninsula mostly in the Cape Espenberg lowlands for many years. So I know the region quite well since then. So since 2008, I conducted first fieldwork there. But in 2013, I came back to Germany, took over the research group lead here in Potsdam for permafrost at the Alfred Wegener Institute, which is the German Polar Research Institute. But since then, I'm still connected to Alaska. I do regular field campaigns in Alaska, and I'm really happy to coming back every time, basically. Yeah, and so since 2018, 16, 18, I also continued based out of Arvi with fieldwork in Western Alaska. We worked on the Seward Peninsula and the Baldwin Peninsula, but also the adjacent mainland areas, the Noatak, Kobuk regions, and so on. And I will show some of the data that we have from there. So our research institute is a non-profit polar research institute. So we are not a company, but a non-profit entity. We are not a university, but I'm affiliated also with a university. We do permafrost research with about 50 people here. The whole diversity of permafrost research that you can think of, from remote sensing to biogeochemistry of permafrost, coastal erosion of permafrost coasts, fluxes of gases, greenhouse gases, for example, but also water and energy fluxes. We study paleo-environmental environments in permafrost, looking at the sediments and cores from permafrost. So very different things. We have a lot of labs here in Potsdam as well, where we can analyze samples. And we have a lot of infrastructure that also helps us with processing remote sensing data. For Alaska, we collaborate very closely with UAF, of course. I have personal ties there with many collaborators and friends. But we also work in other regions, not just Alaska. So northwestern Canada, for example. In the past, we worked also in Siberia quite a bit. Not anymore since 2022. Our focus is on permafrost, ground ice, and disturbances. So what is changing in the landscape, what is rapidly changing in the landscape especially. We look at these dynamics, at the processes behind that, and how that affects ecosystems, but also infrastructure, and so on. So the impacts on the hydrology, on lakes and streams, on the biogeochemistry, on carbon, for example, on vegetation, as well as the coastal settings. And so we are interested in both the local, but also the global feedbacks from these changes. A few general words about permafrost for those who are not that familiar with permafrost, maybe. Permafrost is distributed largely in the northern hemisphere. So we're looking at the map here, showing a distribution of permafrost, and we see Alaska with lots of permafrost, northern Canada, and the biggest portion of permafrost is actually found in Siberia, and a little bit more in the Central Asian high mountain areas. There's a tiny bit of permafrost in Europe, even in Germany, but it's really minuscule. So the largest permafrost region in the Arctic found there, and what we see on the right is a typical permafrost landscape in the Arctic tundra. That's from northern Alaska, actually, with these so-called ice wedge polygons. And so permafrost is defined by temperature, which is different from all the other parts of the cryosphere. So ice sheets, sea ice, snow, glaciers, that's all defined by ice. Permafrost is only defined by temperature, and it's any ground that remains below 0 degrees Celsius for at least 2 years in a row. And that's 32 Fahrenheit. By that definition, about 23% of the entire northern hemisphere land area is underlain by permafrost or affected by permafrost. In some areas, especially in Siberia, permafrost can be very thick, more than 1.6 kilometers, which is about a mile thick. So that's crazy to think about how deep permafrost can reach. What we see here is a satellite image already, that it shows typical permafrost landscape features like these ice wedge polygons, but also degrading, thawing ponds, small pools of water that form because of the melting of the ice in the permafrost. And there are larger lakes. And on the left side of the image, we see the coast, basically, and along the coast, we see slumping because there's lots of ice on the ground. The coast is collapsing there. Permafrost itself is, it's frozen. What we see here is a cross section basically, and this bright part, this whitish part here, is a so-called ice wedge, a feature of massive ice that is found under these ice wedge polygons. And on top of it is the so-called active layer, the seasonal layer that thaws every summer and freezes every winter, which is not part of the permafrost. And on the Baldwin Peninsula, for example, this layer can be 1 foot to 2 feet deep, approximately, so 30 to 60 centimeters. In the high Arctic, northern Alaska, it can be 1 foot, but the farther south you go, it might become thicker. In some other areas, we have lots of ice on the ground. That's a part in Siberia, a landscape with Yedoma permafrost, old Pleistocene permafrost. And you see these massive bodies of ice here. These are also ice wedges. It looks like a glacier, but these are actually ice wedges. And there's a person for scale here. So these are sometimes walls of 10 meters or 30 meters height even. We find something similar in Alaska, but not as extreme in terms of the ice content. So here are a few examples from Alaska, and showing also the map of the distribution of ground ice in the permafrost region. This is a picture from the permafrost tunnel in Fairbanks, actually, where you can walk through permafrost, and you see those ice wedges from below, actually, and you see the massive scale of those ice wedges. That's the dark gray areas here that are shiny. And in between, we have frozen sediment. So in this case, it's frozen silt. It contains a lot of bones, actually, from the Pleistocene, from the Ice Age, and also grass roots and other stuff. And also small ice lenses, like we can see on a small image here. So even the sediment next to these big, massive ice bodies contains ice. And so some areas contain ice which exceeds more than 80% by volume. And so if you imagine that this permafrost thaws and loses 80% of the volume because the ice is melting and it's going away as water, then there's a big subsidence or sinking of the landscape happening. And so the map basically shows areas where there's high ground ice content and medium ground ice content. These are the areas that are especially vulnerable to melting ice. All the ice is basically relevant for local to regional processes and for infrastructure, of course. There's one process or one feature in permafrost that is relevant on a global scale also, and that's the carbon pool stored in permafrost. So vegetation living on permafrost, basically in the tundra or even the forest regions, dies off and gets included into the soil, and at some point might be included in permafrost. And this happens over a long time because permafrost preserves organic matter really well, because it doesn't rot, basically it doesn't decompose so much. And so it gets included into the permafrost, and over time, over hundreds or thousands or even tens of thousands of years, we accumulated a lot of organic carbon in these thick permafrost deposits in Alaska, Canada, but also Siberia especially. And so if you compare the storage of carbon, organic carbon in permafrost soils and sediments, it's a huge amount on a global scale. So we calculated with colleagues also that the carbon storage in permafrost is about 1,300 billion tons of carbon that is stored there in this permafrost region. And for comparison, our atmosphere currently contains about 880 billion tons of carbon. And the global vegetation, all the forests, everything, contains about 520 billion tons of carbon. So the amount of carbon stored in permafrost is almost twice as much as we have in the atmosphere currently, and way more than we have in a current living vegetation on Earth. So because of that, it's a relevant carbon pool if we have warming and permafrost thawing. Some of this carbon might be mobilized and be turned into greenhouse gases that go into the atmosphere and contribute to further warming. And that's the so-called, we call it a positive feedback loop as a scientist, because the warming of the air temperature which we see in the Arctic already warms the ground temperature. That enhances microbial activity in the ground, and that produces greenhouse gas emissions, methane and carbon dioxide, and it goes into the air and enhances the warming further. And that's something that we need to study to better understand how permafrost change contributes on a global scale to climate change. So permafrost thaws in step with a rapidly warming Arctic. Change in temperature in the ground at 2 meters depth between 1997 and 2019 is shown here on this map. And we see these reddish areas here, especially in northern Siberia, that show temperatures there on an annual scale is about temperature change 0.2 degrees Celsius in these red areas. That's very minuscule, but it's per year. So if you calculate it on a per decade base, that's several degrees Celsius that changed already in northern Siberia. And it's getting close to that also in northern Alaska. So the rise in global temperatures in permafrost regions is especially strong in the Arctic, and that's also causing the subsurface ground to warm and thaw. So, and that's also what we can measure. So there are many boreholes in the Arctic permafrost region by many colleagues from different countries also that monitor permafrost temperatures. And what they observe is basically a rise in temperature over the last several decades. And it's a steady rise. Sometimes there's a little bit of plateauing, it's slowing down, but then it's continuing. So right now we have the warmest temperatures in permafrost in many of the boreholes that we ever recorded for the last 30, 40, even 50 years in some areas. And in some of these boreholes, we are getting close to thawing. So especially in regions like Western Siberia, more central and Western Alaska, but also in some areas of Canada, we see permafrost boreholes crossing that threshold of freezing or thawing in this case. What does that mean, thawing permafrost, especially if it contains a lot of ice? There's a lot of change happening. So that's an example from Siberia. The thawing of material, we have the loss of this thick old ground ice. We have deep thaw subsidence. And with that, we also have to change in hydrologic systems. So lakes are changing, they are growing, they are draining, rivers are changing, and streams are forming or draining new systems. And we have the release of this very old carbon from these thawing areas. Of course, there's also an impact on infrastructures in the Arctic. So infrastructure is like roads or pipelines, but also settlements. And that's an example from northwestern Canada here, the Dempster Highway in northwestern Canada going to Inuvik. And we have very big thaw slumps next to the highway already. So the thaw slumps thaw into massive ice and are eroding towards the highway here. But in Western Alaska, there's also risks of thawing permafrost, and there's thaw slumping there. There's coastal erosion, and that's just an example from the city of Kotzebue. Many of these shoreline segments around Kotzebue had to be enforced with seawalls and so on to prevent further erosion. But in other areas, other villages, they are less fortunate so far. There are many relocation plans currently executed. Coastal erosion in permafrost regions is speeding up. That's what we observe in many regions. Here an example also from the Canadian Beaufort Sea. It's very similar on the Alaskan Beaufort Sea side. Erosion rates in the 50s to 70s were very small, on the order of 1 foot, a little bit more than 1 foot, or 0.4 meters per year. And then they doubled by the 70s to 90s. Doubled again in the 90s to 2000s. And then in the most recent periods, they are exceeding even 10 meters per year in many places. So we have a massive speed up in erosion rates for various reasons. One reason is also we have less sea ice cover in these regions. The ocean water gets warmer, and of course air temperatures increase as well. So and that also enhances thawing of permafrost along the coast, which then erode faster. So there are lots of risks from thawing permafrost. because this large region is covered or underlain by permafrost, the permafrost is warming rapidly and thawing in many regions. The resulting changes impact not just ecosystems, but also infrastructure. Arctic communities are affected increasingly and are threatened by thawing permafrost. And this permafrost carbon pool is important on a global scale for our carbon budget. However, there are some opportunities also to look into this. So we have some new cutting-edge research approaches that we can use for studying permafrost, for better understanding how fast these changes happening, and where they are happening, and what the consequences are for ecosystems, but also for infrastructure. So with the automated observations, remote sensing, that's what I'm going to talk about mostly in the next couple of slides. And then also, yeah, use of artificial intelligence with large data sets and modeling methods. But also the other side of the medal, people are living in the Arctic, of course, and you know it best. Many of you are living there, and maybe living on permafrost. So community-based observations and knowledge is really important. So co-production of knowledge for scientists with local communities and partners is really essential to observe and understand and quantify what is happening actually there and what the best ways would be to mitigate or adapt to these changes. Yeah, so why Western Alaska? So there are many permafrost regions, but Western Alaska is especially interesting from a scientific perspective also, because we have a very strong gradient of permafrost from the southern portion of Western Alaska, so the Yukon-Kuskokwim Delta, crossing the Seward Peninsula and going into the Baldwin Peninsula and Noatak region. So we have less permafrost in isolated and sporadic permafrost in these regions. And then we have discontinuous permafrost on the southern Seward Peninsula and go into continuous permafrost in the northern Seward Peninsula and these other areas. So there's already a gradient of different permafrost types. Permafrost is more patchy in the south and more solid in the north. But this will also change dramatically in the coming decades. And that's what these maps show. They are a product of permafrost modeling. And they show that already by the 2050s, many areas on the Seward Peninsula, for example, will start losing permafrost. And then by end of the century, most likely large portions of the Seward Peninsula will be free of permafrost or have only very spotty permafrost left, given those warming scenarios. And that's what we already see with some of the field data and field observations that other groups, here in this case from the University of Alaska Fairbanks, what they are collecting and seeing in their boreholes across Alaska, and especially in Western Alaska. So the map here shows basically locations of boreholes. So every dot is a borehole. And some of these dots are blue. So there's permafrost and no thawing observed. And there are some boreholes that are yellow. And these yellow boreholes, they actually show a development that is called talic, which means that the seasonal active layer starts thawing deep enough that the winter doesn't freeze it completely anymore, which means that the permafrost and the seasonal frost layer actually disconnects, and it's a so-called unfrozen zone that develops. And once this takes hold in some of these boreholes or areas, things change dramatically there. So in terms of hydrology, in terms of biogeochemistry, and so permafrost is doomed in some of these areas already, because the climate today in most of these areas is not suitable anymore to really deeply freeze the permafrost anymore. So how do we track permafrost thaw with remote sensing? Our goals are basically to provide spatially consistent and continuous tracking of landscape changes in permafrost regions, and to provide some quantitative observations of these local to global changes. So we look at local scales, but we also use data that looks at the entire Arctic, for example, for permafrost landscape changes. And our methods for the local scales is mostly using airborne data and ground-based campaigns. So with optical imagery, we acquire images from airplanes and from drones, but also from ground-based terrestrial laser scanners or GPS measurements and so on. So they are very high resolution, very high precision. And then we also use satellite-based methods using images that are available for the entire Arctic for a long time period already So we can look at the regional to pan-Arctic changes, and we can combine those different scales from the local high resolution scale to the moderate to high resolution pan-Arctic scale. And in the bottom of this slide, you can see a few processes that we can observe with those images and those data sets. So tundra and forest fires, for example, this is a fire scar in Siberia, river erosion, thermal karst, so subsidence of permafrost settlement because of the ice thawing in the ground. Then lake drainage is an important process, and lake expansion, thaw slumping, especially along coastlines, but also in hill slopes on the Baldwin Peninsula, for example, along the coast. Coastal erosion itself, with big blocks falling off, or coasts being eaten up by the sea. And then, of course, infrastructure changes we might also see with those data sets. Yeah, and jumping right into the airborne campaigns that we are conducting in Western Alaska. So it's actually not just in Western Alaska. So since 2019, we are conducting more seriously those airborne campaigns. And I will also have a quick outlook on 2025 and 26, where we will continue those campaigns. So our goal for those airborne campaigns is to monitor accelerated thaw of permafrost, so rapid processes, coastal erosion, but also some of the ecological parameters that we can see in the imagery. Yes, we do that with our own airplane, actually. And this is the RV Polar 6 airplane. In this case, it's parked at the Ralph Fiennes Memorial Airport in Kotzebue in June, so a couple of weeks ago. We finished our campaign for this year. Here's the campaign team. And the campaign team is quite international, so we have Canadian pilots and mechanics and a German science team in this case. And in the upper right, you can see the Polar 6 airplane in flight at survey altitude. So that's how it would look like from the ground if you spot the plane flying over permafrost regions. It's a fairly big plane for these kind of surveys. It's actually a modified DC-3. So DC-3s are very old planes. So the first of those were designed in the 1930s. And actually, this particular plane had a plaque saying 1943, I think, was the construction date on that plaque. However, they are modified. So it's a Basel turbo prop engine now, and pretty much most of the parts in the plane are new now, except the frame. So they are really suitable for polar research. So they are used over ice sheets in Greenland and Antarctica, but also over the sea ice with different types of sensor configurations. And we started using them in 2019 more extensively for campaigns over permafrost regions. So it's the big advantage that our institute has those planes. They are on regular flights or pretty much all year round. And for some of this time, we can use it for our purposes for monitoring permafrost. There's a quite big crew in the plane, so there are lots of scientists in the back, 3 to 4 sometimes, that operate the instruments in the back. And I'll come to that in a second, what kind of instruments these are. They're usually 2 pilots that are flying the plane, and they switch places because it's sometimes very tedious to fly those patterns that we require for the monitoring. The sensors that we operate are multispectral cameras. So we take imagery in the red, green, and blue. So this is optical, like a human would see it, but also the near infrared, which is sensitive to vegetation and to water. So that's especially good for separating those different types of surfaces. Since last year, we also have a thermal infrared camera, a TIR camera, that is sensitive in the temperature, in the higher temperature range. So we can sense surface temperatures. And for all these campaigns, we use also laser scanners, so LiDAR instruments that sense surface elevations at a very, very high precision. And so these surface elevation can be used to construct elevation models, which then can tell us about the characteristics of permafrost thaw features And if we fly multiple times over the same area, we can detect change in these features. So we can see whether thaw slumps are growing, whether coasts are eroding, and we can quantify the volume of these changes. Since this year in 24, for the first time, we also have a new LiDAR system on board that actually not just does the topographic laser scanning, but also is capable of bathymetric laser scanning. So it's a green LiDAR system, a different wavelength, and this wavelength can penetrate into water and can sense the depth of the water, depending on the water quality, of course. So that's different for different types of water bodies. There are lots of challenges with that, of course, in these kind of environments. Some of the water bodies are very murky, lots of sediment in there and algae and whatnot. And so that's something we test out, how well we can use it for detecting depth of lakes, of streams, and near coastal areas in Western Alaska. There are a number of additional sensors that are variable with campaign. So sometimes there are other types of sensors included, sometimes not. Here just a few examples, other types of cameras, but also radar systems or methane sensors that we sometimes use on board. So, but the main instruments are the cameras and the laser scanners. So the main targets of our interest are land surfaces and characteristics. So landscape dynamics, thaw subsidence, fire scars, lakes. But we also look at changes driven by beavers, for example, damming up rivers and lakes, and also settlements and infrastructure. And in the near coastal environment or nearshore environment, we look at coastal erosion, but also sediment plumes in the water, and hopefully bathymetry starting this year. Most of our campaigns are actually taking place in end of June to mid-July. That's the ideal timing for most of these areas here, if there's not too much rain. So in this year we had a lot of rain, unfortunately. So the timing was maybe not that perfect, but we need snow-free season, of course, and we need a season when the vegetation is not already dying down in fall. So sometimes earlier in the summer is definitely good for us. For the camera systems, it's really important that we have no clouds. Hazy and smoky conditions are bad. It was a big issue last year, for example, in northwestern Canada, because we had lots of wildfires in northwestern Canada, also close to Inuvik. And there was a lot of smoke in the region, which also interfered with our flight plans. Yeah, then we have other issues with low clouds. That is an issue, or even patchy clouds. Sometimes it's difficult if the clouds are moving very fast, because we treat and process the data in a certain way that we later mosaic many images, thousands or tens of thousands of images, and then moving shadows of clouds is a big issue for processing those data. So and for the laser scanning, the rain is sometimes an issue. In these areas, we fly different patterns to create larger areas that we cover with our data. And mostly we do these kind of grid patterns, which we show here in the upper right. So the plane is basically circling over a specific area for a few hours sometimes. And then within those parallel lines, we have our target area where we have a high density of data acquisition, of image acquisition, and collect a lot of information basically for those areas. And also for the LiDAR, it's a very dense point data set in the end. But sometimes you also follow lines like coastlines or rivers or roads. And then it looks like in the lower image here. That's an example from the Canadian Beaufort Sea along the Yukon coast in Herschel Island up to the Alaskan-Canadian border. So to monitor coasts, this is a preferred approach here. We usually fly in 500 to 1,500 meters height. That's about 1,600 to 5,000 feet above ground, so fairly high. But the resolutions that we achieve with our imagery is up to 5 centimeters, up to 5 to 10 centimeters sometimes. And for the laser scanner, it's up to 15 points per square meter. So that tells you about the density of laser detections per area on the ground. We fly also fairly slow with 120 to 130 knots. It's not possible to go much slower, and the plane would stall. But slow speed basically helps with data acquisition over these areas. Yeah, going into the data and what we acquired. So here are the examples from Northwestern Canada, very small acquisitions of data in 2018, but then a larger area was covered in 2023. And then in 2019, we did Northern Alaska, and in 2021, for the first time, Western Alaska. And so in 2024, we, for the first time, basically repeated measurements from one of these campaigns. So we pretty much covered or tried to cover the same study areas that we had already in 21, which will allow us to look at the data and compare it directly. So we have 3 years difference, and this will give us an opportunity to look at changes in these permafrost features in landscapes. Yeah, overall, from these 5 campaigns, we have more than 2.5 million images acquired and more than 70 terabytes of data. So it's a huge amount of data that needs processing. And yeah. So all these campaigns are, of course, not made in thin air and just by RV, but it's a collaborative effort. So some of the sensor systems are developed by the German Aerospace Center, the DLR, so the camera systems, for example. And other partners are involved in the field campaigns or the aerial campaigns and the selection of target sites for the surveys, because those other institutions have already ongoing field surveys or have ongoing work there where they do observations for many years, and then we add to those observations with our airborne missions. So for Alaska, that's, for example, also for the US Fish and Wildlife, the Selawik Refuge, for the National Park Service in the Arctic national parks, as well as Barren Land Bridge, for example. But then we also share data with the Northwest Arctic Bureau and yeah, provide information to others, like the native village of Kotzebue, for example. The research output so far, we have a number of Bachelor of Science and Master of Science theses that are working on this or already completed, looking at specific questions, scientific questions, like, for example, the processing of the data, or the evolution of thaw slumps along coastlines, or coastal erosion. There are a few scientific publications out now, not too many, but we are expecting this to grow fairly quickly soon. Yeah, we share data with local stakeholders, as well as reports on the expeditions and field work and the progress. And so the data sets for the imagery is already available on Pangea. It's a data archive, and people can go there and look up the data. It's still in review, basically. So we are awaiting final confirmation from the journal, basically, that the paper that is associated with the data set is accepted finally. And then hopefully the data set is completely freely available. So the LiDAR data is still in the works. It still needs to be processed. And we are not finished with that yet. So for Western Alaska, the surveys, again, the map showing here, there's a strong focus on the Baldwin Peninsula and the Seward Peninsula here, with many areas, but we also covered parts in the Selawik Wildlife Refuge, as well as the Kobuk and Noatak national parks. And some of the villages here that we also covered, apart from Kotzebue, we covered Selawik, Kivalina, Noatak, Shishmaref, and many others. So the data here, yeah, the image data in blue, green, red bands, as well as the near-infrared band. Many coastal areas were surveyed. And that's an example of an image mosaic from the Cape Blossom area. It's on the south of Kotzebue, in the northwestern corner of the Baldwin Peninsula. It's a cape with very ice-rich permafrost, and it's also of interest because a road is being constructed towards that area, and it's supposed to have a harbor, a deep water port built at some point. But we noticed that the erosion rates are quite high in this area, and we'll show that in a second. Yeah, so for the 24 campaign, so the same area 3 years later, we covered very similar places basically, or the exact same places to be able to compare it. It shows the different weeks that we were surveying, week 1, 2, and 3 in end of June and early July. And some of the examples from 2021 can be seen here. For example, from the Selawik Thaw slump, an optical image and elevation model derived from image mosaics, so from stereophotogrammetric processing of those images, which are strongly overlapping. You can see the structure of the Thaw slump, or one corner of the Thaw slump. Here's another example from Kivalina, small village in northwestern Alaska, on the Chukchi Sea coast. Seeing that we also can recognize the buildings in the elevation model, and here polygonal tundra in another area. So the status of those images is they are currently fully processed. They are awaiting the final publication of the journal paper, but it's already loaded onto the data archive on Pangea. The first data set was already shared with the Northwest Arctic Bureau for that region, especially with the 40 communities that we covered. So a little bit more detail on some of the data sets. The Selawik Thaw slump, a very big thaw slump developing on the Selawik River in the Selawik Wildlife Refuge. You can see the optical data here. The near-infrared image shows the wet area of the thaw slump. And in the elevation model, we see also the subsidence in that slumping area. Our data was also used in a recent study looking at lake drainage west of Kotzebue. So on a property, a small lake drain that was used as a freshwater resource for the people living there. And so what we noticed basically is that in the 50s, this lake was growing until the 2000s. And then in 2021, there was still a big lake there. And this lake actually disappeared in 2022. So it pretty much was going away, draining through a small channel into the sea, into the Kotzebue Sound in that area. And then the lake was completely gone by late summer in August 22. So we happened to be there at that time in 22 for some field measurements. And our colleague Ben Jones from UAF actually went to the lakeside and was able to do a drone survey and look at the initial changes there. And we were able to fly over the lake so the year before in 21. And so now in this year in 24, we flew over it again to see how it changed afterwards. So that was a really nice discovery, which was made basically by the people living there and using the lake as a freshwater resource, the Schäfer family near Kotzebue. And they made a lot of observations on the lake drainage event itself and what happened after lake drainage before the scientists basically got involved. So a very nice example of how this plays together actually in making observations of a changing landscape that is dramatically changed. What we see here is a difference between elevation models. So between 2016 and 2022, these elevation models were subtracted, and we see that basically there's a big erosional channel forming that has formed where the lake drained, and this channel is actually still growing. That's what we observed in this year, in 24. Another example from Kotzebue here, a mosaic of images showing the detail that we can see. That's, of course, not the full resolution here. Full resolution would be about 10 centimeters in the visible imagery, but also in the near-infrared and the elevation model. Okay, Blossom I showed already. Again, here the optical images and the near-infrared image. Another example from Kivalina, showing the detail of housing and coastal settings. Also showing the stone wall protecting Kivalina here in that area, and some port facility, docking facility, and evacuation road. Another example from Selavik, a little bit farther inland. Selavik is also located at a place where there's many rivers entering the Hotham Inlet, basically, or the Selavik Lake first. So there's lots of water. It's very flat, the landscape. This is having an effect on the permafrost there, of course. So there's many lakes, many polygonal ponds that are growing, and the rivers are changing also strongly. So this is a comparison between 1955 and 2021 from our airborne campaign. Shows quite some dramatic changes. For example, the village itself was growing since then, but also old airstrip was turning into a lake over that time. And some of these areas, like the spit here on this island, was eroding, and other changes that we can see in detail include, for example, ice wedge degradation at a building in Selavik. So this is the same location actually. So there was no building there in the 50s. The building was built there, and at some point ice wedge degradation started right behind the building. This might be due to snow accumulation as well. This is the small spit, the northern spit on the island in Selavik. It's eroding. And so some of the houses might have to move fairly soon. There's the construction of the new runway on the other side of the river, which we can see here. And there's some formation of small ponds in between the runways. And then there's one lake east or west of Selavik that has been growing dramatically also over time. Yeah, apart from those airborne data sets, and I was only able to show a few examples here out of these many test sites or target sites that we had. So we expect much more information coming out in the coming months when we are able to compare our new data from 24 with the 21 data for the first time. What we also did in between, since 21, basically in the year 22 and 23, we went there with ground campaigns and studied some of these features in more detail on a very local scale with drones and with field measurements, like with this LiDAR system that we can carry in a backpack. And then we also created elevation models and maps out of these data sets. So this is something we can compare also with the prior data from the airborne campaign from 21. So comparing with the drone data, elevation models of the same locations, and we can see if we subtract those elevation models, we can see changes in these coastal areas. So there's a gully, for example, that is subsiding and eroding, especially also the Thaw slumps are eroding, and there's a little bit of accumulation on the slump floor here or at the base of the slump. So that's useful information to learn about how fast they are growing and how much volume is being moved by those slumps. And with the new airborne mission from 24, we will have that information for much larger areas or larger sections of the coast, for example, on the Baldwin Peninsula, but also the Seward Peninsula. Yeah, so for 23, we did similar things on the Baldwin Peninsula, but also in the central Seward Peninsula. We mapped additional features, especially drainage gullies and drained lake basins. But we did also some greenhouse gas measurements in some of these areas. Yeah, with that, I would probably close the first part. That was all about the airborne missions and the local scale observations that we conduct with our Perma-X campaigns. And I would like to go into the more pan-Arctic scale. Pan-Arctic scale is also relevant for Western Alaska because the tool that we are developing, the Arctic Landscape Explorer, is available for free use, and it can be used on the local scale also. So it's basically a tool that uses satellite data to detect disturbance trends, so changes in the landscape that are rapid and are associated with abrupt permafrost degradation. So pretty much the same changes that I talked about before that we monitor with airplanes cameras and laser scanners. We are trying to see with satellite data, and so going to the bigger scale here. So what we do is we provide maps marking those different types of changes and having this online tool, the Alex tool, to visualize those changes. So everybody can go there and visit in their own region, their own community or campsite, and have a look at what is changing at this site or in the surroundings. So, and the data source for that is basically Landsat. So it's a satellite system from NASA USGS with a very long time series at 30-meter resolution. 30-meter resolution is moderate resolution. It's not very high, but it's still great for this large scale that we are looking at the entire Arctic. We're using mostly images from July and August because they are snow-free mostly, or often cloud-free, and can be used for our analysis. We're covering the entire Arctic, which means we're looking at 10,000s of images and multiple terabytes of data, which requires a lot of processing and high-performance computing. So the analysis that we do is we look at the entire time series of Landsat for a 20-year period. So from 2003 to 2022, it's the most recent period that we are looking at. So that's 20 years, the recent 20 years. And we developed an automated change detection procedure that looks at every individual 30-meter pixel in this entire region and derives changes in the pixel characteristics or properties. So the reflectance that the satellites detect. And so what this tells us is basically where we see strong changes in the land surface because they affect the reflectance and pixel properties. A big challenge for us was like, how do we condense this information, which is very complex, very large, into a simple map that can be used by not just scientists, but by everybody who is interested in looking at these regions and who might be affected by those changes. So how can we visualize those changes and the degree of change in a single map? So what we do is basically we conduct a so-called Tassel-Cap transform for the multispectral satellite data that gives us the greenness, the wetness, and the brightness information. And we look at the change in this information over the 20-year time period. And so if we put all this together into one data set, we create a colorful map, like here on the right, which has very flashy colors. And the more flashy the color is, the more substantial the change is. And I come to that in a second, what those colors mean. So basically, we have a color triangle that has as the corners basically the greenness on the lower left, the wetness on the lower right, and the brightness in the upper corner. And so wherever a pixel trend falls, it goes somewhere in this triangle and it shows the trend. So for example, if we have a drying trend, we go from blue to yellowish. If we have a wetting trend, we go from yellow to blue. And what that means is actually in our map that features that become drier turn out yellow. For example, lake drainages. So if a lake disappears and drains in the landscape, it's a bright yellow spot. The opposite is true for erosion or flooding. So there it becomes a blue spot or blue area. So in this case, it's coastal erosion on the Drew Point coast in northern Alaska. The same here for vegetation. If vegetation decreases, it becomes more pinkish, purple. And if the vegetation increases, it becomes more green in the map. And so this is an example of fire scars, in this case in central Siberia. And it shows many different types of colors. There are more greenish colors and there are more reddish purple colors. And this is because those fire scars have different ages. So some of them are really fresh, where vegetation recently decreased because it was burned. And some other areas are already recovering from the burn a couple of years ago or several years ago. And so there we see a vegetation increase in a different color. So we see this mosaic of different burn scars. And then we have surfaces that become brighter, more reddish in our map, or darker and more turquoise. And there's an example of an open pit gold mine in Fort Knox in central Alaska near Fairbanks. Where we have brighter surfaces here in the mining pit, which turn out really red. Or in northwestern Canada, the setup of a road here, for example, there's vegetation decrease because the road was built over the tundra, which was there before, and now it's a bright surface. And here it's a gravel mine that turns out red as well. And there's some infrastructure changes in Inuvik, new housing developments that also turn out red. So we can see all those changes in one map and can use that basically in a website that we developed to browse around and look at those different changes and see what has happened in my area. So we designed this website, the Alex tool, with in mind to have very fast loading times and being used under low bandwidth conditions. So especially for Arctic communities also, that they can use this tool. It can be used on desktop computers, but also mobile devices. So you can use your iPad or laptop or even cell phone. There's a QR code, but also a link here. Very simple one. And so you can check out what is happening around my home, my community, my research station, if you're a scientist, but also around my campsite or cabin. So what we do, and maybe I jump over this here because of time. So there are a few additional layers that we can use in the Alex tool. And there's not just the change map with these flashy colors, but there's also additional maps that show high resolution satellite images. There's a topographic map that shows place names, and there's also an elevation model, I think. So we can also look at those changes individually, not just as the flashy color map, but also we can look at brightness changes or greenness changes or wetness changes specifically. There are a few tools in there that can be used to measure, or if you're somewhere out there with a cell phone and have cell phone reception, you could even use the locate yourself on a map tool, and then it finds you on a map, and you can look around what is actually changing in the landscape where you're actually standing right now. This is how the tool looks like, the website. So on the left, you have a map view. On the right, you have a story map view that explains some of the changes that you can observe. This can be closed by clicking on the small arrow here. Then you have the map view only. And so there are a few points here where we can switch the background map, for example, to satellite or topo. You can use different devices. That's what I mentioned already. And before I close, basically a few more examples how that looks like in Western Alaska. So this is Nome. So some of you are familiar with Nome or currently in Nome. There is a Nome right now. So we see different things. So there's surface mining happening in some areas around town, quite a few areas actually. There's beaver damming in some of the streams and valleys north of town and west of town. There's revegetation of former mining sites, which can be seen here. And there's also construction at the runway, basically, in Nome. Because the time period covers only 2003 to 2022, the effect of the Meerbok storm is not included in these maps yet. So we will see that only in the future update of those maps, because it's at the very end, what happened at the very end of our time frame. For the Northern Baldwin Peninsula, examples from the Kotzebue area. So again, for the village, there has been quite a few changes over the last 20 years, including the runway extension, for example. There's beaver damming in many places on the Northern Seward Peninsula. So beavers are expanding quickly and rapidly and affecting many of the streams and the small ponds there. But there's also lake drainage. So we see these many yellow spots here, very large lakes that completely disappeared over the last 20 years. And then there's erosion. And so if you look around the coastline here of the Baltic Peninsula, one of the fastest eroding areas is actually the Cape Blossom region. So Cape Blossom here on the lower corner, and then the low-lying area next to Cape Blossom. And this is actually where currently the intention is to build this port facility. So the road right now goes until Sadie Creek, which is about here. So it's about halfway. And the big question is like how to deal with that and whether this is a feasible thing to do. Yeah, Shishmaref, another example with coastal erosion. So sitting on a barrier island, very vulnerable, of course. And so the barrier island is eroding at the front here. There are some sediment redepositions in the back of the island, but there's also some lake drainage happening in the hinterland on the mainland. Hooper Bay, further south in Norton Sound, there's also erosion and deposition happening. So this orange color is more deposition, the blue color is erosion, and there's quite a bit of flooding, and this is probably also the effect of storm flooding here in this area. And I think that's one finally here, Kivalina and Point Ley on the northern part of the west coast of Alaska. Again, very vulnerable with those erosion things taking place. On the barrier island, and a little bit of infrastructure construction. We can see the road, the evacuation road, and the road to the Red Rock zinc mine, for example. And Point Ley, one thing that happened fairly recently, a few years ago, is the drainage of the freshwater lake. That was important for Point Ley because it was tapped by the river, and that's shown up here as an orange spot. Yeah, so mapping those local changes is important. And of course, we cannot go to all these local changes and see what they actually are. We have a good understanding for some of them where we have been ourselves as scientists, but of course, local communities and people living in Alaska and Canada and Siberia, they know much better what is changing in the landscape. They have a much better understanding of what is going on. And so it would be very interesting to come together basically and get feedback on what people think is changing there, or whether they know things are changing. And so we are thinking currently about expanding this tool in a way that people can add their own information to it. So they can tag certain features that they know about, where they have seen lake drainage, for example, where they know there's coastal erosion, or where they know there was a fire happening. And so that would be very valuable for us as scientists, of course, to validate those maps, but it would be very good also for the communities to let others know what is happening in their landscapes. So the question is like whether people from the communities would participate in that. And so we are trying to initiate community consultations. We did that in 22 and 23 in Kotzebue and Nome to some extent, talking to various stakeholders and people in these communities. Presented some of the ideas of the early versions of the tool, and we are planning we did this in this year as well in 24 actually, and so we are planning to come back in 26 the next time. So hopefully we get more feedback on the usefulness of this tool. And so the big question is, what applications would people living in Alaska, living on permafrost, potentially see for the tool? And it would be great to get feedback on that, on the usefulness of this tool, and whether this is something that can help you with either developing a business or helping adapting, mitigating some of those dramatic changes. There's a small survey also that can be filled out if you're interested and have used the Alex tool, which would also help us getting more information about how useful it is or what could be changed to enhance it. And with that, I think that's my last slide. Kayanak Pak. Thank you very much for your attention.
All right. Well, thank you so much. I learned a lot. And before we go any further, so for the Strait Science audience, this is your time to show Guido a lot of love. It is now 5:30 in the morning, and he's just completed his Strait Science. So thank you very much, Guido. I mean, honestly. And so drop some love in there for him and his efforts here, and then we'll open it up for questions. All right. All right. Let me look. You got nice comments on your graphics, and I have to say those were stunning.
Thank you very
KB,
much.
this was very interesting. Thank you. So I'll start off with a question just to get us going. One of the shocking things was seeing that airstrip in one of those overheads. I mean, just thinking about that for a second, that turned into a lake, right?
Yeah.
How that was like the 50s until when?
Yeah, so the airstrip in Sellerbek, that was an old airstrip. So I think it was like used before the 50s even. So already in the 50s there was water somewhere.
Okay.
So it was a very old one, I guess in the 30s or 40s. And then since then, I mean, now it's a clear lake, a full lake, basically. So it
So
took a couple decades. Yeah.
okay, so it was like asphalt, or it was one of those metal.
I'm not sure actually.
Oh, you're not sure.
I'm
Okay.
not
I just
familiar
wondered
with.
if that acerbated having that structure on top of the soil. Is that what heated it up faster there?
Yeah, I cannot really say like what the original
Okay.
for the airstrip was, whether it was like a dirt strip or just yeah.
I was just thinking, how quick is it going to take? When you say some of this is hitting near melting right now, that's what it looked
Exactly.
like, right? In your
Yeah.
boreholes, and you're
Yeah.
measuring in there, and it's like, ooh, it's getting close to melting. So how quick, once it hits melting, how quick are we going
Then
to see things like that?
then many of these things will happen much faster. Yeah, definitely. And that's only getting worse, I guess, in the next decades. Because we see the temperatures rising in permafrost, so that's really observed, and especially Western Alaska has very high permafrost temperatures. Like in the Nome area, it's just below freezing in some places.
Yeah,
North on Seward Peninsula, it's like minus 2, minus 3 degrees Celsius. Not very cold. No.
right.
I have a question.
Go
Yes.
ahead.
Go ahead. Yeah, hi, my name is Susan Apasingok. I'm from Gamble.
Mhm.
I love to travel the island
Mhm.
and ride the tundra a lot and notice a lot of soft ground and permafrost melting, and
Mhm.
also breaks in the ground all over the tundra that have never been there. I'm wondering if the Alex app, is it an app?
It is an
It
app.
is an
Yeah.
app. I'm wondering if the app will show the ground temperature when I get to camp.
It cannot show the ground temperature at this point. So we are thinking about how to make that possible. There's one data set that we can include, but it's very rough. It has a 1 kilometer resolution, which is really coarse. So it could be used to get a sense of the general temperature of permafrost in one area, but not at a very specific location. So that's something we are thinking about how to enhance that. Where there's a possibility to include ground temperature, because it would be a very valuable information for many, I think.
Okay, yeah, my camp is 17 miles south of Gamble.
Okay.
And
Okay,
so,
I'm not sure if there's a current permafrost monitoring site in Gamble. I would have to look this up. Mhm.
yeah, because I notice a lot of swamps too that have never been there. There's a lot going on, so yeah,
Yeah.
it would be a good idea to
Okay.
monitor our permafrost too.
Yeah, so it would be interesting. I mean, definitely try to have a look at the Alex app and see whether you can see the changes in that location also in the app. And then you could also send us feedback. So sometimes we don't know exactly, we know it for thaw slumps or for fires or for lake change, but some of these changes, like getting more swampy, it would be very interesting to learn about how this actually looks like in the images, in the maps. So if somebody like you from the location, from the village, knows exactly, okay, this is swamping, getting more swampy, getting more wet since many years now. This would be very valuable information for the science side also.
Thank you.
Thank you.
Yeah, thank you, Susan. There's a lot of change in our region, as you know, but St. Lawrence Island, it's really noticeable. There's even you know, I think there's been a landslide. There's all kinds of things that are coming undone because of the melt, this big thaw.
Yeah.
So the satellite would cover all that? Like you could I haven't tried to look at your Alex
Yeah,
site
so
and to get
Lawrence
there.
Island is also covered, St. Lawrence Island. Definitely, we don't have anybody on St. Lawrence Island currently, like participating in these observations. But of course, it would be very interesting. So if people from St. Lawrence Island are on the call here, I don't know if Deanne made a comment, is from St. Lawrence Island, and it would be very interesting. We know that lakes are changing a lot dramatically in Western Alaska since many years now. There was a big event in 2018 where many big lakes drained on the Baldwin and the Seward Peninsula in 1 year because it was a very wet year and a very warm year. And so with all the rain that Gay also mentioned, like in the beginning, there could be things ahead that change the landscape dramatically because of the rain impact also on permafrost. And I think it's very similar on St. Lawrence Island because it's fairly close and a similar setting.
Yeah, the ground is very, very soft.
Yeah.
Thank you.
Thank you. And there are several people from St. Lawrence Island on the call. With their hand up, go ahead, Gnome Nugget.
Hi, thanks for your presentation. I was going to ask about societal engagement, and I'm really impressed by the Alex app. That's really great. You spoke of community outreach to get people to use the app. What does that look like? And, when you come to Nome or COTS, and also where else are you advertising use of this so people in Arctic regions know about it?
Yeah, so on the one hand, so when we plan our campaign, we try to be in touch with different community entities or stakeholders before we go in a region. And it's different for Alaska versus Canada, for example, or the North Slope is also different like compared to Western Alaska. And based on those contacts, we then try to meet them also when we are in the region or in the communities for the campaign. So we meet with them and talk about the development of the tool, but also our campaign goals, and then try to get feedback how they think this could be useful for the communities. So, and just a few examples. I mean, because we have been based out of Kotzebue mostly, but have been traveling through Nome, we visited people in Nome. So on the campus, for example. And then in Kotzebue, we had contact with the borough. We provided data to the borough already from the 21 campaign, the city, native city of Kotzebue. Then also with the radio station. So we try to communicate about those permafrost issues and the campaigns, but also the tools that we develop through the media, basically. So it would be great to spread the word. And something similar we do in northwestern Canada, in Nunavik, for example. Yeah.
Yeah, that's great. And my only follow-up is, are there tutorials to use it online? Or do you think it's simple enough that it's self-explanatory?
Yeah, so there is a little bit of a tutorial in the tool itself, which can be started. So it guides you through like what options there are. We try to keep it fairly simple. So it's really designed, in our view, for non-scientists. So for regular people interested in looking at changes and seeing what is happening actually in these regions. But of course, it would be good for us to also get feedback whether that's actually the case, so whether things should be enhanced or simplified. If things are too complex, then we try to come up with solutions. So getting that feedback would be very important for us as well.
Excellent. Thank you.
So Guido, just as a suggestion, I don't know, the Northwest Arctic borough, as a borough, and the North Slope borough is a borough, and the Bering Strait region, no. So it's a little more, we have the tribal landholders are in native corporations, both,
Yep.
we have a regional corporation, and then we have 20 tribes in 16 coastal communities that have corporation lands. I would imagine, I would contact every single one of those in the Bering Strait region. The landowners, just from that side of things, I think people would have a lot of questions, just like Susan did, and different uses on how they might utilize your
That's
products.
definitely a very good suggestion. And we were trying to get in contact with Nana before, or Manilok. So far
That's
unsuccessful.
Kotzebue. That's Northwest Arctic borough.
Yeah, this
Yeah.
Northwest Arctic borough.
That's not us.
But it probably was also at a time where we couldn't really show something so far. But now we have something to show.
Yeah,
So the tool is working, and so now I think it's the time to really share the link to the tool and get people to have a look at it at least and see how it is useful for them, and including in the native corporations, because they have land management tasks as well, and they have environmental units.
yeah, we have Coeric as well as
Yeah.
a tribal consortium, and then we're so glad to have you tonight and to learn more about what you're looking for and what you've done. I think this is something that would have there'd be great interest to see what's going on in people's backyards for multiple purposes.
Yeah.
So I hope
And
we
I
can
mean,
help you
there might
there.
be some purposes that people come up with that we don't even know about or think about.
I'm sure there are, without doubt, actually, without a doubt. All right. Any other questions? And the caller, sorry, caller, you haven't, I forgot to bring you in right in the beginning, but you knew you could jump in at any time. Is there any questions specifically for the caller? Thank you for your patience, caller. If not, that's okay. For my other question is, when are you coming back, Guido? I mean, you've just finished this. Are you done and that's it? And this is the end of, this is it? Or are you coming back to do more to the region, to the Bering Strait region?
Yeah,
Or
we
is it
come back to
just
do
lucky
more.
Kotzebue?
And no, we come back to do more. And we actually wanted to go, even during this campaign in June, July, we wanted to go farther south with our surveys. We couldn't make it because of the weather. There was too much rain, too much clouds. We couldn't get to the south coast of the Seward Peninsula. We wanted to go to Nome, survey there, and also like Shaktoolik, Elim, these areas. We couldn't make it. So our plan right now is to come back in 2026 with the airplane. And for the next campaign, I would consider actually being based out of Nome. So to have a little bit more coverage of these areas in the southern region, because we didn't do that so far. And it would be great, like, to have the Northern Sound region at least covered.
Well, make sure you reach out here when you do that. We'll
Yeah,
try to
that would be 2026.
everyone would be interested.
Next year in 2025, we will work on based out of Inuvik for the first portion of the campaign. And then the second portion will be on the Alaska North Slope, because we were there in 2023 and on the North Slope in 2019, which would then be like 5 or 6 years later. So we try to cover repeated areas.
Okay. Oh, I also have a last question. Well, one last question, I hope, and that is you had shown some of your flight paths for your LiDAR camera and your green LiDAR, which penetrates into the ocean or the water. And it looked like you were doing flights. Those weren't transit. Those were actually data gathering over the water. It looked like when you were going off the Seward Peninsula, kind of Espenbergish or somewhere towards, you had Kotzebue further ahead in the northeast direction, but is it because we're so shallow you can actually get the bathymetry of the ocean bottom there? And then what are you looking for ice on the seafloor and measuring the change there, or what's going on with those offshore ones?
No, yeah. So it's really a test. So it's the first time we had this green LiDAR system on board. And in very clear water, it's supposed to go, yeah, up to 15, 20 meters deep.
Okay,
But that's most likely not the case in these kind of environments that we have here in the Arctic. So the water is very turbid, it's very dirty sediment, lots of sediment. So
lots of good algae, along with
lots of
some
good
other kinds of
algae,
algae.
yeah, or bad algae. So we really have to look into like how deep we can actually see. I don't think that we can look deep into the Kotzebue Sound, like these overflights between Kotzebue and the Cape Espenberg lowland. But in the near coastal areas or areas in front of Kotzebue, basically the channels there, we hopefully see something and see bathymetry. But yeah, we also have to deal with the data first. We haven't had a look at it so far. There might be some issues. We have to look into it.
All right,
So we are hopeful, but we can't promise anything.
all
And we
right.
did a bit of testing actually. So there were some people out with the boat at the same time where we were flying. So they were measuring depths, for example, in water quality parameters, so that we can also compare this and use it together with the airborne data.
All right. Well, thank you very much. And thank you all, the participants, the Straight Science audience. Thanks for tuning in. Next time we're going to have a Straight Science is going to be, it looks like it's still in the works, but it looks like August 22nd. NOAA has some underwater glider robot things that are taking all types of measurement under the surface. Might be nice for you to meet up with those people and do your LiDAR on
Yep.
on one of theirs. So anyway, we'll send out the announcements when that is finalized. And thank you so much all for coming, and we'll see you next time.